Kourtis from Princeton University here. Okay, good. Speaking about combining correlation with topology and
And then I asked her to check her record.
All right. Thank you very much. Thank you all for being here, and let me also thank the organizers for putting this really nice conference together. I'd also like to thank them personally for giving me the opportunity to be an ICON fellow. It has been really great for me the last 1.5 years. So, yeah, I really thank the ICON people once more. This is the title of the proposal they wrote for this ICON fellowship, and you can see it's sufficiently vague and ambitious. So the first part was carried out in the University of Cambridge. My mentor there was Stefanos, and the second year I am now in Princeton University, and working with Andre Bernavik. So let me acknowledge also my mentors and also my collaborators, Jan Lee, Juman, and Dani. And these are some abstract art from these works here. So I think we live in very exciting times in condensed matter generally, and especially when you go to nice places like Cambridge and Princeton, it's hard to resist to work on a variety of things. So these are the 4 directions that I've been involved in. The first 2 are from Cambridge, the second 2 are what I've been working on in Princeton. And then I was thinking it would be very hard to give an overview of all of these in this short talk, so I'm going to focus on one of them. But let me quickly tell you about these 4 directions that I find very exciting. So the first one is the prospect of realization of the topological order in cold atoms. So recent experiments showed that one can realize topological bands in optical lattices, and then the next question that one wants to ask is, can we partially fill those bands, introduce the ethics of interactions, and try to get a topologically ordered state? So when one starts treating the models that pertain to these experiments, one gets terms that effectively can be thought of as kinetic constraints. And Claudio, what we did was trying to see whether these kinetic constraints, which are now different than, say, density interactions, whether these can induce topological order. So, and we found that indeed, even with these kinetic constraints alone, one can induce topological order in these systems, in theory. Of course, experiments are more complicated, but there's a strong push, let's say, in this direction, so hopefully we'll have some experimental results also soon. The second topic is quantum spin ice, in particular excitations and their dynamics in quantum spin ice. We heard a bit about it yesterday, so basically we're motivated again by experiments which show a broad continuum of excitations, magnetic excitations in the last neutron scattering, in materials like the 227s, terbium titanate, or praseodymium zirconate, and so on. And there the question is the following. In classical spin ice, we have a swing to out rule, in every tetrahedron, and then basically flipping a spin generates this pair of excitations, monopole and manipulable, and then one shows that thermal fluctuations make these deconfined and make these fractionalized excitations relevant to degrees of freedom. Now, the question is, what happens when one has quantum dynamics instead of thermal? And this is in particular pertinent to these materials where the magnetic moments are smaller. And yeah, motivated by this, we asked the question, okay, let's introduce one such excitation in this system with quantum fluctuations and see how do they behave. Do they behave like a or not? Now, in Princeton, these are the two big things, at least in condensed matter currently, I would say. One is Majorana present, what we'll talk about. There's still work in progress, we're trying to figure out whether correlations play a role in these nanowires. And the second is Wowsing method. So Wowsing method is a novel class of topological materials, and they're a density study. They've been studied with photo emission quite a lot, and here we're interested in basically alternative signatures beyond photo emission. I will explain why. So I'm going to focus on this for the rest of this talk, and let's see how far I get. So Weyl metals are materials that have Weyl in them. Electrons close to these Weyl behave as emergent Weyl fermions, and this is by saying this, and people get their kicks out of saying that these are Weyl fermions. And so, we'll be presenting some work on this. But first, let me quickly explain what is a Weyl metal. The answer to this question kind of depends on who you ask. So for me, a Weyl metal is just this, K dot sigma. K is the three-dimensional momentum. Sigma is the vector of the three volume matrices. This Hamiltonian gives rise to two bands that have a linear touching at K equals 0. So energetically, this is it. But of course, there's more to it, which has to do with why we call these materials topological in the first place. And the reason is that each of these Weyl nodes, shown here as this small circle, small sphere here, is a monopole of varying temperature in K space. So this is what people, how people put it. But essentially, what this means is, if you define your wave function, you can evaluate a quantity that looks like a vector potential in K space, then obtain the corresponding magnetic field. And what you find is that if you integrate it over a surface in K space that encloses the Weyl node, you end up with an integer. So in this sense, these materials are topological, right? And then this has consequences for the boundary of the material. First of all, to put these on a lattice, you always need to introduce pairs. You cannot have a single monopole of anything in real matter. You need to have an anti-particle. And then basically when you cut such a system and you look at the surface, Fermi surface, you see that you have open contours that connect the projections of the two Weyl points on the surface. Okay, so in terms of theory, that's pretty much it. Now, if we turn to material science, people tell you that this is a Weyl metal, this structure here, tantalum or niobium, monophosphides and monarsenide. This is a prediction. The material scientists, they draw their spaghetti diagrams, and then if you zoom in enough, lo and behold, you find that you have these band touchings. And for this material, for this material class, you get 24 of them. Okay. So, and then after the prediction comes the experiment. This was one of the first papers that actually showed that one has Weyl nodes in the bulk. You zoom in, so you do ARPES, and then you zoom So how do we detect that these materials are topological? So far, the primary, I would say, identifying feature that people have focused on are these fermions and how to detect them. And this has been done with ARPES. And this is what is shown here. You see these are the projections of two of the vowels, the tantalum arsenide, and you have the state, as we see it here, but it's there, that connects the projections of the vowels. However, we would like to go further, because it turns out that to have the simplest vowel assembly method often used to understand things, one needs to break down universal symmetry, and this can be done either spontaneously or with an applied field. And then when one applies a strong field, ARPES cannot be performed as far as I know. So furthermore, these are surface features. They pertain solely to the surface, so it would be nice to be able to detect them with a dedicated surface probe. And this is what this work was about. And basically what we see is, what we want to do is detect unequivocal signatures of fermions in scanning tunneling spectroscopy, particularly the quasi-particle interference patterns. And this is what I show you here. This is from a DFT calculation, and this is a calculated UPI pattern that emerges from this Fermi surface. So this is for the, let's say, 001 surface, and these two lines here, these are the fermions, but you see there's also a lot of other stuff here. Nevertheless, when you calculate the UPI pattern for this, you obtain this characteristic kind of figure 8 pattern, this pinch point in the middle, and then you try to compare this with experiments, and for example, for this paper here, which I show the data here, you see indeed something that looks consistent, but it's not clear enough. For the tantalum arsenide case, it's even more complicated because you have this surface band structure that is a horrible mess. Nevertheless, there are ongoing experiments to try and verify that you indeed find this signature. This is about the surface, but here I'd like to focus about the bulk. So the typical mantra of topological states, topological insulators in particular, tells you that in the bulk you have a band structure that cannot be distinguished from a trivial insulator. This is what we learn in elementary school. But for these materials, actually you have something that is in the bulk that actually carries the topology, and it would be great if we could go directly and measure that topology. Okay? And so this manifests itself as a winding of this very flux. So let's say this very flux, this magnetic field around this point. And ideally, what we'd like to do would be to measure precisely this. And so this winding has been this is a reasonable thing to do, and people have actually done it for the surface of a 3D TI. So there you have, again, a cone, and again, there's a certain structure. I'm not sure if it's visible here. There are some arrows there that show how the pseudospin recesses as you go around the surface. And using either a spin-resolved ARPES or perhaps fancier techniques, one can find actually that indeed we have this winding as you go around. So this is not something totally crazy. But now we want to do it in the bulk, and ideally I would like to do it with a somewhat newer technique, in the sense that, we would like to try something new. And the proposal is to try and do that with resonant inelastic X-ray scattering. So this is a photon in, photon out probe. So you shoot a photon, a highly energetic photon to your material that excites an electron from a coral level into the valence band. And then you have this highly energetic orbital that scatters electrons in your valence band. And then after a certain time, you have a de-excitation, and you get a photon, which you measure. And the difference in momentum and energy between these two photons is basically what you have transferred to your material. So in terms of a valve semimetal, the process pictorially can be seen like this. You get just an electron, you scatter it somewhere. And this can be either elastic or inelastic. Okay, so this is a technique that has been used for some years, and you need to go to a synchrotron to do this. So this is me making very delicate adjustments to the instrument. And then, I mean, of course, you can model ignore all the equations for now, but the point here is that I can control the measurements, especially the polarization of the incoming and the outgoing beam in these experiments. And what I can do is I can isolate the x, y, and z components of the pseudospin, which is what I said is winding around the bound. Therefore, if I can do this, I can see this winding as I go around the bound. And this is what I'm showing here. Here I'm just showing what the spin does. So see, this is the x component, the y component, and then if I subtract the two, I convince myself that I always need to have these two zero crossings. Now in bricks, what I have is scattering from one K point to another K point, and what I have is something more complicated, but it has again a trigonometric form, and again a certain number of zero crossings. In particular, you find that these zero crossings are always 4 times the topological invariant of the node. Right? So if your node has a chart number 1, you will get 4 zero crossings. That's 2, 8, and so on. How does this work for toy models? Well, this is the result here. I should say there is a subtraction involved here for the 2 pseudospin components, but this is something that can be done experimentally. So yeah, this is how this looks. You see here as you go around, this is a Rick spectrum at a certain energy transfer. You see these 4 zero crossings here, 8. This is a double bound node. This is a triple bound node. So this is a way to measure topological invariance directly in 3D. And yeah, so I mean, this is just a demonstration that it also works for tandem marsenite and also for internode scattering. So it's scattered to one node to the other. So yeah, this is really just the conclusion for this.
Sorry, was that data? The last slide was data?
That was its own theory.
That's
a calculation from, I got the bounce from the FTX. And so, yeah, this is basically the conclusion. Stuff happens on the surface, perhaps you can see with SDS. In the bulk, we can measure the winding of the pseudospin around the bound node, and from this we can deduce a topological environment. So, okay, and then just to conclude, these are the topics that I've been working on presently, and maybe just to flash a few things of what I would like to pursue in the future. And thank you very much.
Time for a couple of questions.
So can you show this scheme when you have created this pair of no, couple. Yeah, this no, this one. Yes. So you have create a hole and state in the energy band, and then somehow you keep this state, and without thermalization or any relaxation processes, you create something in the valence band. So my question is, do you have some kind of very unique relation between relaxation time? So you still have this state, and so how it works? Because usually it's just the opposite. Interband processes is much less.
So here you have to hit a resonance to actually have an appreciable signal. And also in terms of how do you model this, this is typically modeled using the Kramer-Heisenberg equation, like the perturbation theory, right? But since you hit a resonance, this means that that term in perturbation theory is resonant, much larger than anything else, and you just use that term. Now, what I showed, these calculations, what I assume is that this intermediate state is very, very short. So instead of putting this perturbation in and actually doing perturbation theory, what I do is I say, okay, this is really a very short time, and I just directly generate the excitation.
So you try to show something which would never happen in some sense. It's some kind of element in your calculations which shows that there is some kind of probability of this close.
Yeah, so this actually is in the femtosecond range. This is really actually very, very short. So,
Okay, thank you. I think we have to go ahead. Thank you.